And hi, and thank you all for being here and listening to my talk. So as Keith mentioned, I'll be talking about using a domain-specific language, or DSL, in Python to implement high-resolution climate model. I'm a software engineer on Vulcan's climate modeling team. Our group started in 2019, led by Chris Brotherton and Oliver Fior. And we're a team of software engineers, atmospheric scientists, machine learning scientists, and our goal is to improve climate models using both machine learning techniques and HPC approaches with the help of several partners, NOAA, Medi Swiss, NASA. We have lots of people that we're working with to make this a success. Vulcan itself is an organization founded by Paul and Jody Allen. And they have lots of tech for good projects in the area of ocean, climate, conservation, and communities, and we're one of them. All of these groups, including ours, are going to soon transition to the Allen Institute for Artificial Intelligence. So if you're looking for us at the end of the year, that's where we'll be. So we know climate models have large sources of uncertainty, partly due to unresolved cloud processes that happen at scales smaller than the grid resolutions at which we can afford to run large climate simulations. We expect that if we could run these existing climate models at 1 to 3 kilometer globally, then we'd be able to reduce this uncertainty greatly and avoid some of the biases we see. The spatial and temporal resolution have a really large impact on the results that we get. So, but if you want to run a 100-year large climate simulation at these resolutions, for it to not take much longer than a month to get through it all, the model time steps need to happen at about 1,000 times faster than real time. That's pretty difficult. So they need to run on supercomputers. But supercomputer hardware is advancing to meet increased power and compute needs in many fields. And the hardware actually has had to change. So many existing code bases often don't take advantage of these enhancements automatically and actually can't take full advantage of the latest technology. Climate models in particular struggle to perform well on the latest hardware. My team specifically focuses on GFDL's finite volume huge sphere dynamical core, known as FV3, which solves equations representing atmospheric motions. It's used all over the place. It's integrated into several models, notably the National Weather Service's Global Forecast System, and most recently the Next Generation Global Prediction System. Its algorithms are scalable, physically consistent, and can be run in a lot of different ways. It's pretty flexible. It's a pretty amazing model. You can run it hydrostatically or non-hydrostatically. You can do a global run, you can do a regional run, you can do nested runs. It's pretty powerful, a pretty powerful model. FE3 is also very fast. It compares well to other climate models or dynamical cores. But it's only fast on specific hardware. It's been designed to be fast on CPUs. And now supercomputers are having more and more relying on GPUs to get the most power. And FE3 doesn't actually do that well there. It can't take advantage of the increased parallelism and higher memory bandwidth that you get there. Now, groups have already been able to prove that you can actually make FE3 run well on GPUs. You can add a bunch of open ACC statements to your code. On the right here, I'm showing an example. It's not from FE3, it's from Cosmo, but it's the same idea. You can add statements to your Fortran code that allow it to parallelize differently when run on GPUs. The problem is that this typically actually slows down the performance when on CPUs. So you end up with this problem where, are you gonna litter your code with different if-else statements for different hardware platforms, or are you going to have different versions that you have to maintain if they ever change? And then what do you do when the next hardware advancement happens and you need to add even more code to your model just to try to get it to perform well? So our goal is to demonstrate that we can improve climate models, both its performance and its maintainability on supercomputers using a domain-specific language. So in the first year of this project, we rewrote this dynamical core, and now we're working on iteratively improving the performance and making the DSL better. And our goal is to have a demonstration high resolution run on a supercomputer. And we're specifically targeting CSCS's supercomputer in Switzerland, PISDITE, for our high resolution runs. So imagine being a scientist working with a model, and you realize it'd be really helpful for your next paper to add or change a calculation to test some hypothesis in that model. You probably know the math version of what you'd like to represent. And you may also know how to discretize it for the grid that model has. You probably are pretty familiar with that model. But you also right now in most models have to decide how am I going to apply this calculation over the whole grid. You have to decide the loop order, you have to decide make the scheduling parallelism choices, and you really end up having to optimize yourself for whatever you're running on. And then as mentioned, it's not portable to be fast on all different machines. So that's the role a lot of scientists have right now. And that's a lot of burden on them. We can actually take away some of this responsibility by using a domain-specific language, which is basically a language designed to solve a specific problem. We give it the responsibility of optimizing your math, and then you get this nice separation of concerns where the model developer is still responsible for specifying the numerical algorithms, but it's the responsibility of the DSL to generate and compile code that's fast for wherever it runs on. Then in theory, for the model to run efficiently on some new hardware architecture, the DSL has to be updated. Somebody has to do the work to make it run fast there, but the actual model code doesn't have to change. You don't have to introduce all this complexity into the actual expression of what you're trying to solve. So it should allow the scientists to spend less time focusing on the code and get to more rapidly iterate over trying different algorithms. And for those of us that really do love wearing both hats of performance engineering and scientists, I know it's a long history of us scientists doing both. I know I'm one of them. I love to have my feet in both camps all the time. It doesn't mean you can't contribute to the DSL, that you can't be part of that. You just have a way to separate, like keep your model code safe from those optimizations that you work on. So general purpose programming languages like Fortran and C++ traditionally have been the standard for HPC. They do strike a great balance between being general and having great performance on CPUs and have helped advance science for decades. But by themselves, they do need intensive user specification of low-level details to perform well. Domain-specific languages, on their other hand, will sacrifice some of the generality you get from these more general languages, but they support a certain set of algorithmic patterns important for the domain and are able to really implement them well and actually focus on, oh, sorry, something fell, and do these really well. So that's sort of the space we're trying to move into. The DSL we're using for implementing the FE3 dynamical core is grid tools for Python, also known as GT4Py. If you watched Stefano's talk yesterday, he talked quite a bit about it as well. We chose it partly because Python has a growing presence in the atmospheric science community. We use it a lot for data analysis, for making figures, and as you saw in the past talk, we're starting to have more machine learning tools. So it's a great language for science to be able to work with. And so we can leverage it for modeling as well with the use of a DSL where the Python code isn't actually what's run when you run on a supercomputer by itself. It'd be way too slow to actually achieve the performance we need. But as a front-end interface to specify code, and then giving that code to a DSL that will generate fast code somewhere, it's pretty effective. So we've been working on the port of this FE3 to GT4Py. We contribute to GT4Py. It's in progress. It still has some features it needs. It's worked pretty well for us. But we don't own that code, but we are contributing to making it work for our use case. Here's an example of how code can look when it's been ported from Fortran to GT4Pi. GT4Pi removes the expression of looping over 3 dimensions and instead assumes the math that you're specifying is meant to apply over the whole domain. And you do have ways to reduce the domain through calls to what we call a stencil. But as you can see, the green loops that we have over FX, FY on the Fortran side disappear. Also, the parallelism specification disappears, and you end up with a lot less code. The vertical dimension is special in GT4Pi, and that's why this with computation parallel interval here is to help deal with the fact that we do have different kinds of algorithms in the vertical than in the horizontal directions. But it's meant to make our lives easier. Really important is that we get overhead-free reusable functions. So instead of trying to get the best speed by copying and pasting math all over the code, that's in Fortran often that's how you get the fastest code, is just to copy it. Having a subroutine has a performance, and here we can have reusable functions because this isn't the code that's actually running. The generated code will inline these, and we can get great performance there. So we're able to actually use some abstraction pretty effectively and reduce the human error that comes with adding duplicate code and changing it. And because this is in Python, you can still escape to Python and do things. You aren't stuck within just this framework. And especially when a feature isn't represented in GT4Pi, that is pretty useful. So to port the FE3 dynamical core, we don't just care about how fast it is, but it needs to actually be FE3. We needed to be really confident that we've reproduced what the answers that it gives. So we developed a framework to help make that easier, to make porting easier, to make sure we are right when we port small bits of code and then build that up over time, so that by the time we have the full dynamical core, we're very confident it's doing the right thing. And if it's not getting the right answer, we have a way to debug and see where the error is coming from pretty easily. So we used another grid tools tool called Serial Blocks, which it's pretty nifty. It lets you just add statements to your Fortran code and comments, well, sort of like you do with OpenACC. But when this code that has comments in it is compiled with specific flags, it turns into code with statements that'll save data when the Fortran code is actually running. So we can actually just generate intermediate steps pretty easily. And then on the Python side, we use the same library to read that data, run our ported code, and then compare the outputs within some threshold. So like I mentioned, we started out with very small units. We built up over time to, by the time we've validated the full dynamical core, we had about 70 regression tests. The first, and this diagram just shows a lot of the different pieces of the FE3 dynamical core. Our unit tests were actually dived in deeper into a lot of these modules, but also have tests around each of these. And this first port, the design was very simple. Our goal was to make it easy on ourselves, even though we had in our mind imagined ways we could design the model to make it look really nifty or slick, to make the porting process less error prone. We use the same module structure, we use the same variable names, and then once it's validated as it is now, we can start to revisit, oh, like, hey, these two things are doing the same thing. Let's try to reorganize a little bit, but we still are committed to keeping a connection to the original Fortran code. So people who are familiar with FE3 aren't completely blindsided if they're trying to look at this. And then also encouraging, yeah, the unit tests are great, but like you can always miss stuff when you're just testing over one time step. So we also made sure that when we run it for longer, here shown is after 6 days running both the Fortran and the Python code, the difference in temperature is actually very tiny, on the order of 1 to the -5 Kelvin. So we're pretty confident that it's a stable result. Of course, it wasn't all smooth sailing, right? It was actually a great learning experience. It would have been great if we could be bit reproducible from the get-go, but actually achieving bit reproducibility can be really challenging. It's possible if you chase after it long enough. It is usually possible, but it reduces the flexibility of what you can do on the new side, and can make you spend like exorbitant amounts of time chasing down things that are on the order of 10 to the -16, which actually do sometimes matter. That's the next point. Like those errors on that level can propagate and turn into errors that are actually pretty nasty and bad when you get to the full die core. So in those cases where we did see that happening, we made those thresholds very strict. And then the other challenge is that not all the code patterns possible that we saw in FE3 were possible to be represented in GT4Pi yet. And that's the main reason why we may see a performance hit initially. And then additionally, the cube sphere geometry of FE3, it's how FE3 has become fast, is by using this kind of grid, which is great, but it doesn't match completely straightforwardly to the GT4Pi model. And we have a lot of specialized computations that we need to make sure happen on those edges of the tiles around the globe. So here I'm just going to walk through sort of how we dealt with those edge calculations. The fact that the DSL didn't quite allow us an easy way to put all those specifications inside of GT4Pi. So initially we had to have separate stencils. So here the different colors just represent different calculations as you get close to a tile edge for the advection scheme. And so yeah, like initially every line there had to have a separate calculation. And then in the Python code, we had to call those separately with different domain specifications. And that's fine, that worked. But we do end up with a lot of stencils. And every time you actually break out into a new stencil, there is some performance cost to it. And so we knew we could do better, but this is what we were able to do with the initial version of GT4Pi. This is what we could do. And so we've actually been working on this feature to be able to specify the regions inside of the stencil. So we give the information to the compiler, and the compiler can figure out how to run it optimally. It can recognize, hey, I'm on the tile edge, I need to do this calculation, or I'm not, so you don't need all those if statements. So we just introduced a language feature with horizontal region, and you specify, hey, iStart. iStart is just one of the indexes in one of the dimensions. If your tile actually has iStart, it's a global index, then it'll run that calculation. If the tile, your MPI rank you're working on, does not have that edge, then that statement is just ignored. So we end up with some DSL code with those same lines with the different calculations, but they're inside a stencil, or here inside a function. And so we end up with less code, it's less confusing to read, it's less error prone. The bounds of some of the variables can get automatically deduced in GT4Pi. And this can kind of reduce the pressure, the arithmetic intensity, and the data movement. So we are in the process of trying to incorporate this feature throughout our code base. And to make all of this work, we had quite a bit of infrastructure we needed to set up and use. That it just made our lives easier. So we were pretty excited about using Docker to be able to have a reproducible environment and be able to run the same code anywhere and get the same answers anywhere. It was really great, and set up our automated testing using it. But then when we were on PysDint, it is possible to use containers there. And we did initially but ended up deciding in the long run just to use a virtual environment there because there were a lot of complications and the container layer was kind of getting in the way a bit. It's not that it's not possible. We just decided for pragmatic reasons to use a virtual environment there. So we have a suite of Jenkins tests where every time we wanted to make a change to the code, we exercise different data sets. We exercise the different backends, GPU, CPU, Python. We run on the different environments. We run tests both that can be run just as sequential units and ones that have Halo updates in them run in parallel. We also have plans to make sure we can keep reproducing our test data because the Fortran repo can be changing as well. And we want to make sure that we can still build our test data. So we're always able to build test data in this other repo and actually use it to test our GT4Pi code. We also run baseline Fortran metrics and performance metrics so we can see how we're doing over time. Just on Halo updates, we implemented using, it's not actually a feature in GT4Pi to do Halo updates at this point. So we need to implement, at least for the Halo kinds of Halo updates we do, we didn't build a general Halo update framework. That would be huge, but just for the ones we knew were happening, we used QPy arrays and MPI for Pi to make these happen. We needed to make sure this wasn't going to be exorbitantly slow. So we did just a little bit of investigation to ensure as we scale up the number of nodes and we have larger problem sizes that the amount of time it takes to run in Python is comparable to what it is in Fortran. The scaling is slightly worse in Python, but it's not extreme. It's right now it's not our largest source of performance hit. So that's good for us. And then when we look at performance of individual modules, we're really excited. We're highly encouraged by what the capability of the GT4Pi is. So we had a student project who actually ported the 6,000 lines of heavily optimized Fortran code that did the microphysics parameterization. And it actually showed great performance. So here, the kind of reddish line is the Fortran code, and the DSL with the light blue line on CPUs, it's comparable. It's not better, but it's around, it has the same performance as you increase the number of grid points. And then the GPU just rocks it as you increase the problem size, it starts to win better and better, which is really encouraging. And then of course the DSL has an option to generate code in Python, which is not performant. It's not meant to be. It's for helping debug, but you can just see like compared, the first dot just goes way off the scale. And so yeah, you don't even use that to compare. It's just good to know like this does allow you some different ways of figuring out how fast you are. But then with the full model, looking at, which is like 84,000 lines of code that have been ported, we are currently very slow. We're not trying to hide that at all. We've been tracking our performance over time, the last month or so. And you can tell the gray line, which is the Fortran, is just looks like it's 0 right now. It's actually 7 seconds. And then the green line is the CPU backend, and the red line is the GPU backend. So up until recently, the GPU backend was actually doing worse than the CPU over time. And then just in the last 10 days or so, we've been doing some refactors that have started to improve things quite a bit. And we actually are pretty confident we're going to be able to get these down to be comparable or better to the Fortran, because we do know there's still several things in our die core that need to be adjusted to be able to take advantage of the DCL. There just still is a lot of code that's couldn't be represented in GT4Pi yet, so it's outside of GT4Pi and being run in Python. So we are just working on features to be able to run those statements inside of GT4Pi. And as soon as you give it to the compiler, it's able to do a lot more. We also work on optimization passes and know we have room for improvement there. There's also some allocation and deallocation of memory that we don't need to be doing. It was just there for convenience because our first focus is on validation. And then there's some memory transfers between CPU and GPU that are happening that maybe don't need to. So we have a lot of avenues for improvement, and we're pretty excited, especially given what we see on the individual module level, what's possible. We're pretty sure we're going to be able to get to better performance pretty rapidly. So yeah, just we're in this cycle of continuous improvement where we look at the performance, we add some features to the compiler, we refactor our DICE core, and we kind of are doing this iteratively as we approach actually having really performant code. Yeah, so just in conclusion, we have an implementation of the dynamical core of FE3GFS in a Python-based domain-specific language. It's portable, so we were able to run it on both CPU and GPU backends by just changing a flag, just making using a different backend. The results show that high performance can be achieved. We're still trying to get there with the full model, but we think it's possible. And we believe we've improved the code by increasing the level of abstraction and allowing us to separate this FE3 code from the specification of CPU and GPU optimizations. So climate models can be fast, performance portable, and easy to understand and maintain using a DSL is what we conclude. I want to thank you all so much for listening to my talk and thank my awesome team. They're a really fun and great group to work with, very intelligent people. And then our collaborators, like so much of this is only possible because they work with us, they help us, GFDL, CSCS, NASA, University of Washington, ISS. We really appreciate all of their contributions. And with that, I'm happy to take any questions.